Welcome everybody to Boulder and to our summer school on C-star algebraic quantum mechanics and topological phases of matter. I'm very happy to see so many speakers and participants from all over, from the US, North America, Europe, and Asia, and that so many followed our invitation. So far we have around 90 registered participants. Organizing such a conference would not have been possible without the generous support we received, and therefore I want to mention those institutions from which we received support. First, I'd like to mention the National Science Foundation, which awarded us a conference grant with which we could support the speakers and a big portion of the participants. This conference is held here in the auditorium of Chilla, and I'm very grateful, or we the organizers are very grateful to Chilla that we can hold our conference here. It was actually pretty difficult to find a conference room because there seems to be another big event on campus, but I think we got a really, really nice lecture hall for that. Then I want to mention the Department of Mathematics, which also supports this event. And last but not least, the CU Boulder Research and Innovation Office, which also provided support for this conference. Now let's go in medias res. Now let's go in medias res and start right away with our first speaker, Daniel Spiegel from the University of California at Davis. And he will give a introductory series to C-star algebras and its applications in math physics.
Okay, thank you, Marcus, for the introduction. I hope everybody can hear me well. So as Marcus said, we have a very broad audience geographically, but also academically. We have people in physics and people in math. I think it's about an even split. And we have people who are postdocs and people who are first-year grad students. So the goal of my lectures is to provide an introduction, a baseline, so that we can all at least understand each other on some basic level. I'm going to be talking about quantum spin systems and the thermodynamic limit. And I'm sure that for those of you who are more experienced with this field, that it will be very familiar material. But I'm also sure that there are some of you for whom this is new. OK, so by a quantum spin system, I'm interested in a system of particles, many quantum particles, that are in some solid state. So they live, I don't know if I can reach that high up. OK, let me divide my boards here. I definitely can. Sven, can I stand on your shoulders? OK, so I'm going to be talking about quantum spin systems, where the particles are quantum spin systems, or quantum spins, individual quantum systems, and they live on some lattice gamma, which I'm going to call gamma. And gamma is just some set, which is a subset of Rd. And for some d, it could be any d. So in your head, you should think of something. Oh, thank you, Mike. In your head, you probably should think of something rather regular, like a square lattice. And at each point, you should imagine there being some quantum spin, which I'll draw in this little cartoon as an arrow. Where the arrow denotes the direction of the spin. And each of these spins is described by a Hilbert space. The state of this spin is described by an element of a Hilbert space. So to each, and let me take these Hilbert spaces to be finite dimensional. OK, so for each point in the lattice, I'm going to associate some finite dimensional Hilbert space. So V here is an element of gamma. And to each V, I associate C to the NV for some natural number NV. OK? And this NV can vary with V. OK. So I'm going to be interested in systems that are very large, that have some macroscopic scale. And so I'm going to be interested in the limit, the thermodynamic limit. which is the limit as the number of particles or number of lattice sites which I'll call n, goes to infinity. OK. So when I'm talking about this limit, I have basically two options. I can either compute everything on a finite lattice in terms of the system size, n, and then take the limit as n goes to infinity. Or I can start with n equals infinity from the very beginning. I can start with an infinite lattice from the very beginning and try and make that work. And that's what I'm going to do. And the reason is because sometimes it's convenient. Sometimes it avoids having to take this n goes to infinity limit. Sometimes, not all the times. But moreover, it is enlightening. It's an enlightening perspective to start with n equals infinity, because there are mathematical phenomena that happen for infinite systems that do not happen for any finite system size, but that we still expect to approximate the behavior of real-world systems, which are finite. Yeah, question?
Yeah, then what can happen if I take n to infinity? In the sense, am I able to cover all of R? I don't know where we're taking the limit.
What can happen?
Yeah, like what is, as we're taking the limit, where are we taking it?
Well, you'd compute some quantity of interest, and you would find that you'd get some formula that has n as a parameter, and then you'd take n goes to infinity, and that would describe the infinite system. So it'd be like a limit of a real valued function, maybe. But it could be, use your imagination. OK.
Yeah, you probably want to repeat the question specific on the recording.
Oh.
I think that one's clear.
OK. All right. So I want to work in this n equals infinity from the very beginning. And unsurprisingly, this has its own technical challenges. And we're going to find that we need a formalism, a mathematical formalism, that is rather distinct from what you learn in Quantum 101. OK, so why can't we just use our usual quantum formalism? So what would we do if we were to use our usual quantum formalism? What's the Hilbert space? So for any finite, do I want to go this way? I think I want to go horizontal first. So for any finite subset of the lattice, which I will denote with a 2 subset inclusions, because I'm going to be using this a lot. So this means that lambda is a non-empty finite subset. We have a finite system Hilbert space, which is the tensor product of the single particle Hilbert spaces. So for the infinite system, it's very tempting to do the same thing and define the infinite system Hilbert space as this tensor product over all sites. OK. But now the mathematician in me has to complain. This is perfectly well defined as a vector space, as a complex vector space, but it's not clear what it is as a Hilbert space or an inner product space. And the natural inner product that you would want to put on this thing might look something like this. So if I consider two simple tensors of vectors in my Hilbert space, that'd be something like this, where omega v and psi v are in the single site Hilbert space. So what would this inner product be? You would want it to be the product of the inner products. OK, but this is an infinite product. It need not converge. So this need not converge. And you could see that just taking omega v to be any unit vector, and take psi v to be minus omega v, and then you would get this inner product would be a product of an infinite product of minus ones. OK, this is nonsense. OK, so this naive Hilbert space approach runs into a problem. And this is why we need a new formalism. OK, so in the usual formalism, we have states, we have observables, and we have dynamics. And states are defined as, well, unit vectors or arrays or density matrices in a Hilbert space, Observables are defined in terms of that Hilbert space as self-adjoint linear operators. And the dynamics are defined, again, in terms of the Hilbert space as these time evolution operators. So which are generated by some Hamiltonian, which is, again, a self-adjoint operator on H. So I think of this as a states-first approach, because I have to define my Hilbert space of states before I can define my observables, before I can define my dynamics. So I think of this as a states-first approach. And I'm going to argue that the approach that we need here is an observables-first approach. So we're going to define everything in terms of the observable algebra. So we start here, and then we define states, and then we define dynamics. And these observable algebras are going to be C-star algebras. And I don't expect you to know what a C-star algebra is. I'm going to tell you. But these are going to be self-adjoint elements of a C-star algebra. And I'll tell you about states in my second lecture. And I'll tell you about dynamics in my third and fourth lecture. And I'm sure we'll also hear about it in some of the other lectures. OK, so we need a C-star algebra. And we need to construct the observables first. So for any finite system, what's the observable algebra? The observable algebra, which I'll call A lambda, is the bounded operators on H lambda. This was my finite size Hilbert space. And this is isomorphic to an infinite tensor or finite tensor product of the single site observable algebras, which are all matrix algebras, and by NV by NV matrix algebras. OK. For the infinite system, let's agree we can only observe quantities localized on finitely many sites. So I mean that, well, hopefully it's relatively clear what I mean. I mean I can only observe observables that are acting on finitely many sites. Then I would take the infinite volume observable algebra to be the span of these simple tensors of matrices AV. This is in gamma, where AV is in the single site observable algebra, and AV is not equal to the identity for only finitely many V. OK, so now this is, again, a well-defined complex vector space. And we have agreed that it is the observable algebra of our infinite system, at least tentatively. OK, I want to emphasize that the finite size observable algebras are embedded in here. Let me call this the local algebra. So this is the local algebra. The finite size observable algebras are embedded in here, where I just take some finite tensor and I just add on infinitely many identities. On either side. To all other lattice sites, I add on an identity. And so on. OK. And then I can see that this local algebra is actually the union of all these finite size C star, or finite size observable algebras. OK. I'm going to avoid using the backboard because it doesn't move. So this has more structure to it than just a complex vector space. In particular, I can multiply two elements. I multiply them factor-wise. And I have a Hermitian conjugation, which again is just factor-wise. So the Hermitian conjugate of this simple tensor is the tensor of the Hermitian conjugates. And I'm using the C-star algebraic convention of denoting Hermitian conjugation with a star. OK, so this is a name. This is called the star algebra. Let me state it precisely. A star algebra, curly A, is a complex vector space with a bilinear associative product. That's the multiplication. And it also has the star operation. This maps the algebra to itself, and such that the following axioms hold. Yeah. No, those would not count as separate things, I don't think, if I understand your question correctly. So I'm unioning. Right. So if A, OK, let me clarify. If lambda is a subset of a lambda prime, then A lambda embeds in A lambda prime. And I consider these just by tensoring on identities. And when I write A loc as this union, I'm considering these A lambdas really are the images of their embeddings. So in A loc, I regard A lambda as a subset of A lambda prime. Okay. Hope that helps. And these are all subsets of A loc. OK, so back to the star algebra. This product and this star operation have to play nice. So first of all, the star operation has to be antilinear. It has to reverse the order of multiplication, just like Hermitian conjugation. And it has to be an involution. So when I do it twice, that's the same as not doing it at all. And this is for all A, B in A and lambda in C. OK. That's a star algebra. With any structure in mathematics comes a notion of morphism between two similar structures. And that notion of morphism we call a star homomorphism. So a star homomorphism is a map, a linear map, which I'll call alpha, between two star algebras, such that it respects the product and the Hermitian conjugation, the star operation. OK, very simple. OK, so we've already seen one example of a star homomorphism, these inclusions where I tensor on the identities. Those are star homomorphisms. There's another very common example, which is called an inner automorphism. Maybe let me say, if A equals B, then we call it an endomorphism. And if A equals B and alpha is bijective, then we call it an automorphism. OK, so there's a very common example of these automorphisms, which are inner automorphisms. First, I want to observe that in a star algebra, I have a notion of self-adjoint elements and unitary elements. So an element of a star algebra is self-adjoint. If A equals A star, and unitary if A star A equals A star equals the identity. Yeah. Yeah. All my star algebras are going to be unital. So all my star algebras have a multiplicative unit, which I write with this Blackboard font 1. So far, yes.
Daniel, is that just pragmatic that we want the identity, or is there like some sort of compactness assumption underlying that we say, okay, we can have a unit?
It's that all the examples I'm going to be talking about have units. Certainly, OK, I personally like C-star algebras as abstract objects. And so I personally care about non-unital C-star algebras. But for the purpose of what we're talking about here, it's not so important. Okay? But I'm glad that other members of the audience also care about non-unital C-star algebras. OK. So an inner automorphism is a star homomorphism of the form A mapping to conjugate with a unitary. And I call this add U. So add U is the name of the map that maps A to U, A, U star. OK, that's a very common example. OK. Good. So we've discussed the algebraic structure on the observable algebra, A loc. But there's actually more structure. There's an analytical structure. There's a norm. OK? So how do I define the norm? Well, for a finite subset, lambda, the observable algebra has a norm because it's the bounded operators on the Hilbert space. And that comes with the operator norm, which is the supremum over all unit vectors of the norm of AX. This is a norm on A lambda. And I can define a norm. So for A in the local algebra, I can define its norm by choosing some lambda such that A is in A lambda, and then defining its norm on the local algebra to be its norm in A lambda. So I have to show that this is well defined. I'm not going to do that. It's easy. So if I had chosen a different lambda, say one that was bigger, lambda prime that's bigger than lambda, the norm wouldn't change. The norm in A lambda would be the same as it is in A lambda prime. Okay? So this gives me a well-defined norm on the local algebra. But it's not complete. So A loc is not a Banach space. I'm free to take the completion, and that's what I'm going to do. And I call this the quasi-local algebra. And I'll just write that as a curly A with no subscript. So it's the completion of the local algebra. OK. There's a good physical reason to do this. It's not just that I like Banach spaces. I do like Banach spaces, but there's a good physical reason. So in the local algebra, we only have observables that are strictly supported on a finite number of sites. So it might have support on 4 sites and be identity everywhere else. But on the quasi-local algebra, our observables are now allowed to have tails that decay to the identity. So they only have to be approximately local. So they could have some decay and support across the whole lattice. Oh, that's B and A. And this is useful because if I even start with a locally supported observable, as it evolves in time, it in general will develop these tails. So as it evolves in time, it will leave the local algebra and just stay in the quasi-local algebra. So this is why it's a good notion to have the quasi-local algebra, the whole completion. OK. The quasi-local algebra. Yeah.
When you say the tails can grow as you evolve in time, is that like just general concept of observables, or is that just something you see that happen?
I would say that it's it doesn't have to happen, but pick your favorite example and it'll probably happen. Yeah.
Can I ask a question?
Yeah.
So in like deep Robinson bound, you get exponential.
Yeah.
Could you make this stricter and look at like a smaller space that's going to contain these exponential scales? And then
You could.
this space looks bigger.
Yeah, you could. And people do that, especially Anton Kapustin and his students. They look at something called the almost local observables. But I don't. This is a little bit simpler. And yeah, this is a little bit simpler for now. I think everything I want to say, I can say with the quasi-local algebra. OK, so this has a very nice structure. This is a C-star algebra. So a C-star algebra, I can finally tell you what this is. It's a star algebra with a complete norm such that the following axioms hold. The norm has to be submultiplicative, meaning that the norm of AB is less than the norm of A times the norm of B. And it has to satisfy a very special property, which we call the C-star identity, or the C-star property, which is that the norm of A star A is the norm of A squared. So this can be proved for the norm on the quasi-local algebra. OK. If you've studied these before, then you know that they are extremely beautiful objects. And I will give you just one small taste of that. Actually, maybe first I should give you 2 more examples. So let me give you 2 examples. Other than the quasi-local algebra, you're at least familiar with bounded operators on a Hilbert space. This is a C-star algebra. A commutative example is continuous complex valued functions. On a compact Hausdorff space. Where the norm is the max which is achieved because it's compact. And if you really want a non-commutative example, or a non-unital example, a non-commutative non-unital example, then you can take the compact operators on H, which is usually denoted K of H. OK, so I claimed that this was an extremely beautiful structure, and let me tell you why now. Yeah. Those are definitely consequences. Both of those are true. It's not equivalent, no.
Sorry, could you explain what's the meaning of a completion and what's the meaning of a complete?
OK, thank you for asking. So the norm is complete. Complete means that every Cauchy sequence converges. And a Cauchy sequence, I mean, so a sequence X, or maybe I'll call it AN. AN is Cauchy if, as m and n go to infinity, the elements of the sequence get arbitrarily close. So this is the definition of a Cauchy sequence. And a norm is complete if every Cauchy sequence converges. Yeah.
For physicists, like you can define something like an exponential function y, right? The property ensures that the resulting object is still
Right. Yeah. So infinite sums like these Taylor series converge to well-defined elements. Yeah, thank you very much. OK, so I've kept you in suspense. Why are these C-star algebras such beautiful objects? Let me give you one taste of this, a theorem. If A and B are C-star algebras, and alpha is a star homomorphism, then alpha is automatically bounded, which means it's continuous. And its norm is less than 1, or less than or equal to 1. And if it's injective, then equality holds. It's an isometry. OK, so this is an amazing fact. The hypotheses are purely algebraic. There are no analytical hypotheses here. And yet, I derive some very strong analytical consequences. OK. And this has implications for the quasi-local algebra. Maybe this is a corollary. This kind of thing happens all the time, by the way, in the theory of C-star algebras. So corollary, if I have a star homomorphism on the local algebra, then it has a unique extension to a star homomorphism on the quasi-local algebra. And B here is any C-star algebra. So why is this a corollary? I claim that alpha is already bounded with norm less than 1. Because if A is in the local algebra, then A is in A lambda for some finite lambda. A lambda is just bounded operators on a Hilbert space. That's a C-star algebra. So the restriction, alpha restricted to A lambda, is bounded with norm less than 1. Hence, the norm of alpha applied to A is the norm of the restriction, which is less than or equal to A. So alpha is bounded. And therefore has a unique extension to the completion. By continuity. OK. So this is really nice, because I can define star homomorphisms on the quasi-local algebra just by giving their values on the local algebra and checking that it's a star homomorphism. And the local algebra is something much more concrete that I can get my hands on. OK. Yeah. Yeah. Oh, I mean an extension of the star homomorphism. So I get some star homomorphism, let me call it alpha bar, which goes from A to B, such that alpha bar of A is equal to alpha of A for all A in the local algebra. Is that clear? Yeah. OK, in particular, OK, so this is how I get star homomorphisms on the quasi-local algebra, starting with a star homomorphism on the local algebra. But how do I get a star homomorphism on the local algebra? If for each finite lambda, I have a star homomorphism on A lambda, and if these are coherent, meaning that whenever I have an inclusion of finite subsets, then I have a restriction. The restriction of A lambda prime to A lambda is alpha lambda. So whenever I have this inclusion, it plays nice with restrictions. Then there exists a unique star homomorphism on the whole local algebra. Such that the restriction of alpha to any of these local algebras is alpha lambda. Finite algebras. OK. So this is one common way, and I'll show you an example of how we construct star homomorphisms on the local algebra. And for those of you who like category theory, this is just saying that the quasi-local algebra is a directed colimit, in the category of C-star algebras and star homomorphisms of these A lambdas. OK. And for those who don't like category theory, you can ignore that comment. OK, so back to this picture. We have the local algebra, which has things that are finitely supported. We have the quasi-local algebra, which has things that have tails that decay to the identity. But this formalism is good enough that it can also handle objects that do not decay to the identity, that are infinitely extended. These will not be elements of the quasi-local algebra, but we can interpret them usually as something different. And what that different thing depends on the object. And let me give you an example now. So a class of automorphisms of C-star algebras that are very interesting are finite depth quantum circuits. And if you Google finite depth quantum circuits, and you look at Google Images, I believe the first hit is something from one of Professor Bachman's papers. And you'll find a picture that looks something like this. So you've got your lattice. And then you've got little bubbles or boxes above the lattice, little bricks, and so on. And then you've got another layer of bricks, and so on. And this can go up. OK, what does this picture mean? Well, this is a lattice. And each brick, if this is the subset lambda, each brick is a unitary that is supported on the sites below it. So these unitaries go off to infinity. They don't have to decay to the identity. What does this mean? I can interpret this as an automorphism of the C-star algebra. Or I can interpret each layer as an automorphism of the C-star algebra. So for any finite union of these lambda 1, lambda 2, lambda 3, I can define the tensor product of the unitaries on lambda 1, lambda 2, lambda 3, et cetera. That's a finitely supported object. I can define the tensor product of u lambda I over I. This is an element of A lambda. And if I set alpha lambda to be conjugation by u lambda, then I can check that I have these coherence conditions. Did I erase them? No, I didn't. So I have these coherence conditions that alpha lambda prime restricted to A lambda is equal to alpha lambda. So there exists a unique automorphism alpha on the quasi-local algebra, which is defined by alpha of A is equal to add u lambda applied to A whenever A is in one of these finite unions. So I've made sense of this infinitely extended object, not as an element of the quasi-local algebra, but as an automorphism on the quasi-local algebra. And if you're me, maybe you abuse notation and call this alpha add a product over all these u lambdas, or u lambda I. This would just be my notation. This product over u lambda i's is not itself a well-defined mathematical object, but conjugation by it is. Maybe I'll put a quotation marks. OK, I think I'm pretty much out of time, so I'll stop there. And next lecture, I'll talk about states.
Are there questions? Yeah, so maybe I come up with a mic that the questions are also.
So those tails, maybe this was addressed by Ryan's question earlier. I guess those tails don't have to be exponential. They can be power law or anything as long as it decays
right.
to.
Mm-hmm.
Okay, thanks.
Yeah, so in terms of for this system where we have infinitely many unitaries, at the level of observables, like what kind of Hamiltonian does that correspond to? Is that still something that exists within the quasi-local algebra, or can we not describe it there?
Certainly. Well, OK, I think we'll discuss Hamiltonians later. But yeah, each one of these things could be generated by a Hamiltonian that's not itself an object of the quasi-local algebra, but it has to be interpreted in some way. Yeah.
Are these algebras we have constructed? All them are UHF algebra, the uniformly hyperfinite algebra.
Yeah. Mm-hmm.
Oh, so what is the physical picture of the universal UHF algebra in this setting?
What is the universal UHF algebra?
I mean, it's in the some sense, it's the biggest one of the UFH algebra you can make.
I'm afraid I don't know this construction.
Okay, thank you.
But I would imagine, I mean, usually we think of having fixed on-site dimensions, and we look at a UHF algebra that is particular to our problem.
Okay.
Yeah.
Okay, thank you.
Further questions? Yep.
If you have symmetry operators that they act like in the whole system, so they don't decay to identity or anything. So we cannot think of these operators as elements of neither of these local or quasi-local algebra. So they would be elements of this something else that you mentioned before?
Right. They're exactly the same. They're exactly constructed like this, except for where each brick sits only on one side. So it's an automorphism.
I see. I see. So you don't think of it as a huge block, but is decomposed into like some tiny. I see. Perfect. Thank you.
Other questions? Yep.
So I guess I sort of was trying to figure out the punchline of the finite depth quantum circuits. And it's basically the idea that you can sort of like go towards the infinite limit if you want, or thinking of more so instead of them as elements of the algebra, you're thinking them as automorphisms on the algebra. Okay. And then trying to use that idea to extend to more things that aren't necessarily in the algebra that you consider instead of doing like we were just talking about, I guess.
Yeah, that's right. So these finite depth quantum circuits are not elements of the algebra. They're automorphisms on the algebra. And in fact, they're not inner automorphisms. So they can't be written as a conjugation with U for any quasi-local U. And from that, you can get lots of interesting things. I haven't talked about states yet, but this helps you generate interesting states.
Perfect. Yeah. Thank you.
OK. Some further questions? No. OK, thank you very much. Then let's thank the speaker again. So we have now a coffee break of 25 minutes, and we resume at 10:20 here. So the coffee and the pastries are outside.